that we just record that. So if you want to have that recording, then as usual, drop me an email and then you can have the link if you want to look into it again. All right, so let's go to our glorious Moodle. And somewhere there is the assignment. All right, good. So, idea behind. So again, the idea is we use our FreeSock. On our FreeSock, we have the duck as a kind of signal generator. We have an ADC on the other side, and now the idea is we want to bring certain signals into our device under test. So in this case now, this will be our bandpass circuitry as it is described down here. And the idea of this assignment is that we want to check if we have the characteristics of the bandpass filter if the characteristics of the bandpass filter are the ones we expect from an, let's say, offline calculation. Okay. First of all, is this roughly understood, the concept? Okay.
Yes, Professor.
Good. Then for this part, there had been some changes. Okay. So first change here is we do not use this, this capacitor here. The original idea of this capacitor was to stabilize this common mode voltage here. Yeah. But I think there was some good reason to remove it, and we simply assume that the supply voltage doesn't have too much noise, so we take this one away. The other change here was that this resistance should change so that the amplification of the second stage changes to 3, so that we end up with an overall amplification of 300. Okay, so now, the problem here is a little bit that we have an amplification of 300, and now the resolution of the deck is so bad, kind of, yeah, that we need to bring in a voltage divider here to break down that voltage a little bit so that we still can work with that amplification of 300. Okay. So we can go into that later on a little bit more in detail on what you have to do here and how this would affect your circuitry. So for this assignment now, the idea is that you select 10 different frequencies which you test your circuit. Yeah, so it's up to you if you want to have this as independent measurements, or if you want to come up with some software here on the PSOC, which is automatically stepping through all the 10 different measurements, right? And is like capturing that. This is a little bit up to you and how confident you feel with PSOC. But the basic idea is you configure the duck. Second, there are more people coming. So the idea is you configure the duck 10 times, basically, every time with another frequency. You stimulate basically that circuitry with that input frequency, and you check what's coming out. Okay, you do this 10 times. Okay, and then you can fill this table, basically. This was the idea here. Okay, then for each measurement, you should in MATLAB get something like that, and then you can read with the FFT what was the highest frequency portion in here. Okay, there's another part of this exercise, which is the simulation. So Professor Banvart simulated basically this circuit here in LT-SPICE. And the idea here is now you have to read in this raw data from the LT-SPICE simulation and to visualize it in MATLAB using this or producing a plot. Yeah. So basically what we want to get out of that are those curves here. The dots you can see are actually measurements he did manually and which he inserted to verify that whole thing. But for your part, the goal is to produce those curves based on the LT-SPICE simulation. Okay, and for this purpose, you have this LT spice to MATLAB function. We can go in that step by step later. I first want to summarize the assignment and the exercise, okay, a little bit. So aim, measure the magnitude response in decibel from the lower 3 dB corner frequency to the upper 3 decibel corner frequency. My recommendation here would be also to check a little bit like left and right of the corner frequency to check if we really have this curvature here. So as long as you can explain what you did there, I do not care too much which frequencies you chose, but I want to have an explanation why you did so. Okay, so Professor Banvart said he wants to have the 10 different test points, let's say, between the corner frequencies. My recommendation would be maybe to have also some measurements with, outside of that, so that we can see that the amplification maybe is not that great outside of our band. Yeah? So to really see if we really have achieved a band pass filter. Okay, so take frequencies spaced equally in a logarithmic scale. Yeah? So up to you to come up with a good spacing here. Now use the deck, for example, the waveform deck, providing the sine wave test signal. So here at that part, the signal is fed into the amplifier input. Okay, the amplifier output is sampled with our ADC, like in the previous assignment, and then this data is transferred to MATLAB so that you can see what happened, right? You can do your FFT and you can see like which amplitude your base frequency, let's say, or the amplified frequency had. Yeah, can read it from there. A few challenges in here for MATLAB. You have to adjust the script in such a way, or your firmware on the PSOC in such a way that we on the y-axis get volts. Yeah. Previously, this had been simply so-called ADC steps. We can talk about that in a second, how to convert from ADC steps to volts. And also down here, we need to have not the number of samples or something like that, but a frequency. Okay, so this is a little bit the challenge here. We can discuss that also in a minute. Okay, constraints, pinning is the same. Sine wave, 10 different frequencies, we discussed that. For the report, okay, the schematic and pictures of the measurement setup. So like in the previous assignment, some pictures simply of your circuitry. Then this measurement table, okay. So basically, here you have this table, and once you have this LT spice, I think Professor Banvart gave that. And now the idea is that you insert the values you have basically measured with this approach, okay? And once you're done, then we have this MATLAB figure, this guy here. And then the idea is that you add your measurement points, like from your table, yeah, you insert your measurement points into this table, and then you can see if this approximately matches our expectation. Yeah, and I can already tell you simply when I see that, yeah, I see all this quantization noise and all that stuff, your result will look different than the calculated amplifier here, but that is fine. Yeah, this is fine. Okay, then again, the PSOC project, though I have to admit, I think I will not look too closely into that, and I have a question for you here, because I was thinking about making a tutorial on how to program, let's say, a template. So basically the second assignment, a solution for the second assignment, to do a video for that. But I think you discussed that in the lecture with Professor Banvart, and he said like, you can use your friend's code or something like that. What is the situation there?
He just told us that we could use anybody else's code, but we'll need to specify in our report that we are using somebody else's code. But
okay, okay. So do you have a fellow student with good code? Because then I do not need to make that video. Also, you have to be careful because I'm taking this as a yes. Yeah. So if you're happy, if you share the code and you have a good implementation, I'm very happy because then I do not need to do it.
So what do you mean by a good code?
A code which is working. I don't care. Yeah. A code where you press the button and you get like this stuff out. I'm perfectly happy with that. I will not focus too much on that. I will more focus on the stuff you do in MATLAB, basically. And on the report, how it's written and stuff. No. Okay, good. So I assume you have a good project. Good. So yeah, then you have to use this PSOC project, also upload that, and of course the MATLAB code. Okay. First of all, do we have questions about the aim or the assignment in general for your task?
Yeah, the PSOC project stays the same, right?
Basically, yes.
Okay.
But we have to modify it a little bit, and I will talk about that in a second here. This vols and
only the deck configuration, I think.
Yeah, you have to adjust the deck configuration, but I think Professor Banvard has he, I mean, like here, you have the specification. Peak to peak, 40 millivolts, sine wave. Okay, yeah, I mean, like this will change, right? This is a bit nonsense. This frequency will change. And the offset of the signal, I would set it to somewhere like VDD half, right? Let's see. Somewhere I have a solution for the second assignment. And then let's simply look into that. This should be the one, because then we can discuss a little bit the configuration and stuff. Okay, yeah, I think the offset again will be like half, right? Half voltage of the deck, because it will not matter too much because again, we have this capacitor here, which will take away the DC anyway. So it makes sense that also for the offset, we take like half of the total range and then simply have our amplitude peak somewhere here in between like that, right? Okay. So make sure that the frequency is correct. Now you have two possibilities to do that. One possibility would be like you configure your desired frequency in here. Yeah, so with playing with the sample rate and the number of samples. Up here, you can see the resulting frequency. You build the project for each frequency, you flash it, you execute your MATLAB script, and then you do this basically 10 times. Yeah, this could be one solution. Okay, you would get like good points for that, but there is, of course, if you want to have a 1.0, then you do need, or you could do a little more, yeah, to get some extra points. And in that case, for example, what you could do, like you take 10 measurements from MATLAB, but every time you trigger a measurement, you do this with another frequency here for the sine wave. And to do that, you, for example, could use this external clock signal. And then you have to come up with some circuitry here on how to produce different clock frequencies, basically, for every run. Yeah, I will not go too much into detail here because this is like if you want to have like the 1.0. If you say like, nah, I have other stuff to do and I just want to pass it, then you simply like do 10 projects with 10 configurations and simply make that run. Okay, good. Now let's talk a little bit about the first problem here. Maybe let's start with that problem. We want to have volts. So if we look into the configuration here, we can see somewhere there's this reference. Okay, here it is. Internal VDDA is our reference. And also here we can see that it's simply abstract VDDA. So how does, or what does the value which we read out of the ADC and which we previously simply passed to MATLAB, what does it tell us? Let's say we have a 16-bit resolution ADC. So this means that the highest value we could read out of it is 65,000, okay? This would mean that this is the entire range, so VDDA plus 100 microvolt is the upper, or the upper limit. VSSA, so ground, analog ground, minus 100 millivolt is the lower bound of our ADC range. So which means if we read the value 0 out of it, this corresponds to minus 100 millivolt, while a value 65,536 would mean our voltage is VDDA plus 100 millivolt. Okay, a value like 20,000 or something is approximately here. Now, the problem is we use the internal VDDA as a reference. The problem here is our results will vary with the voltage of VDDA. So this is a relative value we get out of it. It's not an absolute value which directly corresponds to a voltage, as long as we do not know what the reference voltage was. Okay, and this is a little bit of a problem because even though the PSOC is powered by USB and the specification says, well, USB is 5 volt, in reality, if you do a measurement, it will be 4 point something, 4.4, 4.8, sometimes even 4.2 I've seen. Yeah, so, and this is a little bit a problem because this does not directly correspond. Now, the problem is we could now try to, for example, bypass on pin blah, blah, blah. So the idea here would be you bring in an external reference voltage, or you use an internal reference voltage to say like, I know that this reference voltage which is coming in has a fixed voltage, and you can take that as a reference. That's why it's called reference here, to calculate the absolute voltage, right? Is this clear to everybody? Like where I want to go with that, all that?
Yes.
Professor, just a doubt. Even though if we use the reference as internal VDDA by 4, it will still take the VDDA we have configured at the system, right? So it's like 5.
Exactly. You can, in here, you can define the voltage of VDDA, yeah? And it's now defaulted to 5 volt because this is what we assume on USB, but the reality is a little different, and it might even vary from USB port to USB port. So actually you would have to measure it, or you would have to bring in an external reference voltage. This morning I had a small session with Mr. Hubrich, and he said that there is also somewhere an internal reference voltage we could use. But my recommendation here is to simply leave it as it is, and we have to deal with a certain error, yeah. And then you can simply write in your report, my amplification maybe is a little bit off because our reference voltage for the ADC had an error, yeah. So no need to over-engineer that. But just one question into the round. So how could I, for example, produce a reference voltage on a circuit? So because we're system-driven hardware design, we build a system, okay, we have the problem, our ADC is inaccurate and we want to supply it with a reference voltage. How could we create one on our circuit? Basics of electronics, think about it. Which component can give us a very good voltage, a fixed voltage?
Using a voltage divider?
No, because the voltage divider again will rely on the input voltage. If the input voltage changes, then the output voltage changes proportionally.
Capacitor.
Oh, yeah, there was something. There was something. Sena diet, yeah? So for example, or Sena diet or other diets, yeah? So if you think about it, like for example, LEDs, they have a certain voltage and it's always the same voltage, okay? No matter what. If you have the LED together with a resistor, and no matter what voltage you give into that circuitry, the voltage over the diode will always be the same, okay? So this is fixed. And then you could, for example, use such a small circuitry, so kind of a voltage divider, but with an LED, and to simply use this as a reference voltage, because this is fixed. Yeah. This is one way to do it. Another way to do it is to use so-called LDOs, or simply linear voltage regulators. They are based on transistors, but they basically do a similar thing there, yeah. And they can also give you a fixed voltage, okay. And this was also a little bit the idea here to use this internal somewhere you can configure it. I don't know how this works, but apparently it is somehow possible to take this internal LDO 3.3 voltage as a reference, but I have not looked into that. Yeah. So, but as I said, for the assignment, I don't think you need to go too much there into detail. We can simply say there's a certain error, which is basically based on the fact that our reference voltage is not exactly 5 volt, but we do not have the tooling. You do not have a multimeter at home with which you can measure the actual voltage to configure that, okay? But the general idea where I want to go with that is basically we have an ADC range, then our value range going from 0 to 65,536, so 2 to the power of 16. This basically reflects the entire ADC range. And so if we get a value out of that, this will give us a relative position in this range, basically, okay? Now, for the assignment, it was asked to provide the graph as voltage, okay? Now, basically, you have two possibilities on how to do that. It's a rather proportional or very linear calculation. You simply take that value and you multiply it by 5 volt plus 200 millivolts divided by 2 to the power of 16 kind of thing, yeah? You can do that in MATLAB. So this would be one approach. You transmit the raw data from the ADC as it comes out of the ADC, transfer it to MATLAB, and in MATLAB, you do the calculation manually to volts, okay? Which has a little bit the advantage if you know that, for example, you connect them, you make one test run, okay? You connect those two together without the voltage or without the amplifier circuit, and then you can kind of calibrate that stuff, yeah? Because then you read out the signal, you know what you're expecting, and then you can adjust this multiplication factor in such a way that it also shows your expected values, okay? If this is just 1-to-1. And then you can bring in your bandpass circuitry, and then you know that this is approximately the right configuration for that. Another solution, and I need to get something to drink in a second, is to use a function which you can find in here, which is called counts to millivolts, yeah? Converts the ADC output, so-called ADC counts, the value we just talked about, to millivolts as a 16-bit integer. But this again, as you can see here, is based on this VDDA. when the VREF is based on VDDA, which it is for the configuration at least I have right now, then the value for the VDDA is set for the project in the system tab. Yeah, so we just discussed that, and it will do this calculation on chip, and then you can transfer the values to in millivolts to MATLAB. There's a little bit up to you where and how you want to do that. Okay, so just 1 second, I need to get something to drink. In the meantime, please think about questions, okay? Okay. Whew. Questions, please. This is good. This is good. Okay. So this was this one problem here. Okay. Then another problem will be that our duck, of course, is not an ideal voltage source, which means that it has an inner resistance. And at least Mr. Hubrich said that, I have not verified that, said the inner resistance is something like 4K. Okay, so which means if you connect your circuitry here, your voltage divider, you have to make sure that the inner resistance will not go too much into that whole thing, right? So, I mean, like what you could do, I'm trying not to overcomplicate that, but you could verify that if you first, like I said, you understood that calibration run, right? Where I said, you simply connect basically your output directly to the input, and with that you can calibrate your ADC. Then you know like exactly what is going on. And once you have that, you can bring in your voltage divider here, do the measurement again, and check if the voltage going in is approximately what you expect for the circuitry here. I mean, like if it's just, let me think about it. Yeah, that could be one way to do it. No. So you have to be a little bit careful here, maybe not to use very high resistances, but rather low resistances, rather. Yeah. So don't stress that pin too much. You also might want to look maybe in the data sheet here to learn a little bit about the output and the electrical characteristics of that output. Yeah. So this could be a small problem here. Now, next problem here is that we need this frequency, okay? So where can I find the correlation between the number of samples and the frequency in my project configuration in here?
Samples?
In the which one?
ADC samples?
Exactly, ADC samples, yeah? This is the point here, our samples per second, okay? Because if I know how many samples I receive per second, then based on that, I can, whoops, no, I don't want to show you this one. Then I can calculate back to the frequency, yeah? If I have that. Okay, good. Then let me just briefly, I have to make sure I'm not showing that wrong stuff. maybe let's, how can I show that to you guys? Okay. So the idea here is a little bit in MATLAB that we have again this clear all, close all, blah, blah, blah. The idea is you get, or you basically have this raw file provided, right? You could download it.
So can you make the screen a little bigger because I'm not able to see the font inside the notepad.
Okay, 1 second. Better? Yeah. Okay, so the idea here is like in your MATLAB project. Yeah, so you have a MATLAB, not really project, but you download all that stuff. You download that folder, okay? And then in here, you create a new .m file, okay? And then in this .m file, you can say something like ltspice to MATLAB, which will use this script. In here, you have to provide the raw value or the raw data, basically the simulation result from ltspice you want to read. So this file was given. And the thing is, if you do I have it still open somewhere? I was crazy enough to really simulate that shit. If you do the simulation, then this raw file will contain a lot of different potentials, okay? But basically, we are just interested in a few of them, okay? So, and I think you already discussed that in lecture. Basically, those three, potentials are the ones we're interested in, 5, 10, and 11. No? So this is basically the filter back here where you say, I only want to have this data. And then you can have a look also in MATLAB. You can simply run it as it is right here. And then you might want to have a look maybe at this raw data thing, yeah, and to check what's inside. Because basically this is now simply the data we want to visualize, yeah, and which we can see, where is it? Which we can see, for example, here, yeah. What we can see here is that we have a logarithmic scale down here, okay? So we need to make sure that we do have a logarithmic scale. And here we have decibel. So this is scale 20 times logarithmus log 10, yeah, on that scale. Unfortunately, I cannot help you too much with that because this is now your assignment. And you really, unfortunately, it seems like you have to dig a little bit into MATLAB. I don't want to give you the solution, but what I maybe can do is to name a few functions you might want to have a look at. So, for example, you might want to have a look at, of course, this ltspice to MATLAB. Okay, you might want to investigate a little bit raw data. What is this doing? We need a figure. Yeah, so check maybe what a figure is. You might want to have a look at semi-log x, what this is doing. Yeah. You might want to have a look at title, X label, Y label, plot, and legend. Yeah. And with those functions, you should actually be able to solve this assignment. Okay. Good, 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 good. Yeah, I'm sorry. I know, like, I'm not a MATLAB guru, and I was very happy that there was a solution around already. But you unfortunately have to look a little bit into that. So let's see. Good. I think that should be it for a rough overview. I need feedback, guys. Otherwise, I say goodbye and bye, and everybody is as confused as in the beginning.
Also, just one doubt still. Previously, for the previous software assignment, we used to send 10 samples continuously before we stop the MATLAB simulation.
Mhm.
Is it now for every frequency, one sample is enough? Like one set of receive data?
You
Or-
can do it. I mean, like there are basically two approaches. One approach could be you simply take the second assignment, okay, and you say, okay, I want to measure what are the corner frequencies. Let's see. 100 hertz to what is this up here? What's the other corner frequency?
500 hertz, something around 500.
500, 800. No.
Professor, there are changes in the corner frequency. If you see in the picture on the left side, it's written frequency as 21 to 513 hertz. The left figure, the one in the black one.
Yeah.
Yeah. You could zoom that, the two frequencies specified.
Okay. I mean, like I have not watched the lectures too carefully, so you know more about there are corner frequencies, okay? So, and based on that, you select a few frequencies you want to measure, right? I think we have all agreed on that, right?
Yeah.
Okay, and then you have a table, and in that table you have 10 different frequencies for which you want to measure the amplification. Okay, and now one approach could be to say I'll simply take the second assignment, and then, for example, for the first frequency, I simply configure the DAC in such a way that it provides this frequency. I start MATLAB, I press a button, and it will give me 10 measurements, basically, right? And then I simply take one of those measurements, maybe the one which gives me the best result, yeah, and write that down. Okay. Then in the next step, I reconfigure the DAC to the next frequency, make that run. I get 10 measurements. I'll take the one I prefer for some reason. Yeah, this is up to you. And I write down the values of that. So this could be one approach. Another approach could be to say, and this is like the approach for the guys who want a 1.0. They can configure their software or write their software in such a way that it will, for every round, yeah, it will automatically change the frequency of the DAC in software. Yeah, so that if I press the button once, it will do 10 measurements, but each time with another frequency. Yeah, of course you could do that too. Yeah, but this is a bit more challenging, definitely. Yeah, so you have to decide.
Okay, Professor.
Professor, I have a small question, and I'm not sure if it was addressed already, but could you please go again on how in the second graph the frequency is then, how do we obtain the frequency? Yeah.
Here, so this is the FFT. Yeah, so basically here you see the amplitude on this axis here, right? And here you see the frequency, and you can basically see that for 99.61 hertz, we have a peak here, which means like this. Here we had, or how to explain that? At this frequency, we had a sine wave, okay? We can see this very clearly here, and we can also see which amplitude this sine wave had. Yeah, this is the y-axis. In this here, in this scale, this would be now again decibel. So, and from here we could see, okay, our amplification was minus 33.92 decibel.
Okay, thank you.
to plot this graph, should I do I need to use the semi-log only or plot the below one, the frequency one?
I would say maybe stick to this convention here. So for the part where you visualize basically the measurements from the circuit, there you can stay in a linear scale. I think that is maybe a little bit more readable in that case. But this is up to you. As long as you can explain to me why you have chosen a certain configuration, I don't give a damn, yeah? Because your job is to write a script which is telling me what was the amplification of my test signal. Yeah, that's the only thing I'm interested in. If you have a better solution than that, you're more than welcome. But of course, you have to explain it, and it has to be correct and feasible. Yeah. There, I'm very open-minded. Good thing is, like in the beginning, I thought you have to do an own LT Spice simulation, and I was no, fortunately not. Good. Anything else?
Can you maybe explain again the voltage divider after the deck? How to, yeah, this one.
Yeah. Well, the problem here is that if we look into our deck, so our range selection goes from 0 to 4 volt, let's say simply 4 volt, but this is an 8-bit deck, so which means that we only have 265 values available here. So basically, if we divide 4.08 volts divided by 265, then each bit basically would give us just 15 millivolts. Okay, and I think, has Professor Banvard not even reduced that to 1 volt? Has he?
Yes.
Okay, so because then the calculation basically is 1.20 divided by, so then each step is 4 millivolts approximately, okay? So, okay, then this is the configuration here. The problem is that even those 4 millivolt now, if we would amplify them by 300, let's check that. So it was 1.02 divided by 265 times 300. This is fine, isn't it? Why do we need a voltage divider then? I saw that he did that calculation in the lecture. Wait a second. Was it here? Somewhere he did that as a hand calculation,
Yes,
was it?
it's in the OneNote, in the
the last one, Professor.
Yeah. If you go back.
The last one, no PDF.
Okay. So 4 millivolt, okay, this is fine with me. And we say, okay, now 4 millivolt would be our step size. Then he said he wants to have 40 millivolts so that we have a sine wave with 10 steps, basically. Yeah, so we need to note that our sine wave actually looks like that, right? Yeah. Okay, so 40 millivolts, and then the 40 millivolts peak times 300. Okay, this would be too much. Okay, so this is the problem here, okay? Yeah, because I mean, like, of course, we have a step size of 4 millivolt, but this would be basically just I can't find a picture here, but basically, you know, zeros and ones, yeah, like that.
Yeah.
This is somehow comparable to a sign, but not really a sign. Yeah. So he says 40, right? Because with 40, then at least we have a step size of 10, and then we can see maybe down here that is a little bit more like a sine wave. Okay.
But we keep the peak-to-peak amplitude with 40 millivolts. That's,
exactly. Exactly. This should be the configuration here.
Okay.
But
and then we have to divide it with the, yeah.
Exactly. Then we have to divide it with the DAC, because if we wouldn't divide it, then we would get an output swing of 12 volt. If we amplify the 40 millivolts times 300, we get 12 volts. So this is too much.
Yeah, but what's the limit? Do we have to look it up for the op-amp, what he can, or how can we? Yeah.
This is an LMV 385. The 385. Op-amp. Somebody just posted that here, right? Any of you guys? There it is, Marco Seiler. I also need to check the chat from time to time. Yes, yes, yes. Thank you. Okay, then I'm afraid there are a lot of things I do not really understand, but power supply voltages, input voltage, can we learn something from here? Power supply voltage, okay, no. Frequency, no. Time. Power supply versus. He also said something here, right? Page 4 lists the output voltage limits.
Okay.
3.5 volt for 5 volt supply voltage. So page 4. Okay. Input offset voltage, input offset current, average differential voltage, blah. Yeah, okay, but I'll leave that a little bit up to you, because this is unfortunately, or maybe this page, this unfortunately is a very common task, okay? You design a system, you have to use a component, and you have to read the data sheet, yeah? And you really have to find the value you're interested in. So my recommendation here would be to really look into that, maybe read the data sheet, look for the characteristics you're interested in, and then we can decide, where are we? We can decide what kind of voltage divider we need here to bring that voltage down. But he already gave something, right? Here, 8.3 millivolt. Could that be it? 8.3 times 300. Yeah, this should be right. 2.49. So 0.5 is common mode, and then 8.3. Now, so you have to calculate a little bit like based. So you want to achieve a common mode voltage of 0.5, and that as a swing. And if you have the 40, I'll leave that up to you. There are not too many possibilities what to do with those numbers now, okay? Yeah. So, and this is how you can calculate your voltage divider. As I said, the problem is here a little bit. Somewhere there was this trick where I now could also draw in here. Where was that? Where was that? Somewhere I can draw into that thing now. Can't find it. Damn. Yeah, but the idea, the problem is that here for the VDAC, you basically have another resistance. Yeah, and this is the inner resistance of the voltage divider. So it will go into the play here. But it will only have an impact if those values here are high. Yeah? So if you have a high resistance, then this comes into play. Yeah? If they are comparable low, then the other resistance here is not that important. But anyhow, like check the data sheet of the deck. There should be also electrical characteristics for that. No need to make rocket science out of that, but you should, you know, roughly have understood what's going on here. Well, but this is the specification for the output here. Yeah, and then you can simply do the math. Okay, this is the configuration here. We want to have 40 millivolts configured. How can we divide that in such a way that we end up with approximately 8.3 millivolt as a maximum? Okay, because if we go higher, then I think we're leaving that range here, right? Because then we have 2.5 volt of common mode, and we have, of course, to add this voltage here on top. No? So you have to think a little bit about what you're doing here. Okay, good.
One question, because there's now V in common mode 0.5 volt. Do we have to set the voltage divider for that to get 0.5 volt, or is it?
Well, I would do it in such a way. I would focus more first on the 40. So basically, we're getting out something like this is the wrong configuration here and the wrong offset, okay? But we get an amplitude peak of 40 millivolts out of here, okay?
Yeah.
And we know that we need such a voltage divider to break it down to a maximum of 8.3 millivolt. Okay. So, and this is where I would try to first check, okay, what voltage divider would be feasible to do that job. And for the common mode, then you have to adjust the offset here.
Okay.
Yeah? But because the voltage here is so low that we say, okay, here we want to have 0.4. Yes, it is. What? What? It's the magic of programming. I don't know. Yeah, but here basically you're relatively free to move that around. Yeah.
Okay.
And then I would simply adjust the offset in such a way that it again fits the requirement. This is comparable, easy, right? But we first need to make sure that our swing has the right voltage, because I mean, like this common mode here, it will be filtered away anyway by this capacitor here. So
yeah.
Good. Dabei. Nobody has scope.
Professor, I have a doubt. The values that we are reading from the raw data, or the 5, 10, and 11, are those voltages at different points, or are those gains at different points?
I'm not sure if I got you right, but you mean like the values you read from the ADC, right?
No, the values that we read from the raw data file, from the LT files.
The raw data you read from LT Spice, those should be volts. Those should be volts. I mean, like we can have a look at the slide here. It's calculated into dBs, but let's maybe have a look. Do I have LT Spice still open? I'm afraid it will also give me just also just decibels, and I have no idea where I can adjust that. But I'm pretty sure it's based on volts, and then that calculation is done on top.
Okay. So the Vout one is the output of the first op amp, Vout 2 the second op amp, is it? And the Vout BP is like or what is it actually?
This is out BP. This is then after the second stage. This is, I think, a simulation of the ADC here, and this is this limiting capacitor. Then, so this is the blue one, the overall thing. Then we have V out 2. This is out 1. I guess this one. So this is definitely out 1. So this is the first stage.
Okay.
And the second stage, where is this? Is it this one? It should be this one, right? But then it should be the same as out BP.
Okay, I think the middle curve is the no, the red curve is the gain of the second op amp, only second op amp, 10 dB.
Let's go in here. So this is V out 2. No, V and 0.7, and this looks different. Guys, I don't know. Yeah. I think I know what he did here. He had this simply here is out 2. He did an extra circuit for that, simply to just calculate V out if it would be alone. Yeah. If we simply would take the same input signal, right, but only feed it into the second stage. Yeah, then this would give you this value here.
Okay, yeah, sure.
Yeah, so and then you have like individually the characteristics of each of them. So how can I kick that again? Have I ever told you that I absolutely hate this tool? Anybody knows how I can get rid of that again? Da. Haha. Yeah, so basically the idea is like those are the values that if you give the input signal for each stage, then you would get them individually, and then this V out bandpass totally is like the two-stage filtering of first V out 1 and then fed into V out 2. Yeah. And then this is the result of both of them if you have them sequentially.
Professor, like suppose if we are calculating for 100 Hz, so from this graph we need to verify A1, A2 and A3, correct? A1, A2 and A, correct?
The problem is like you will be only able to measure this output here, right? Because this is the one you're measuring. Yeah. I mean, like, okay, or I'm not sure about that. Like, this is an interesting question. You could theoretically also measure those here if you would plug your ADC into the stage in between. Interesting question. Let's see. Okay. Wait a second. I need to check one thing. So, Mr. Bandwart is also currently in a meeting. I will ask him if you, because my understanding was that you only measure like here, right? And can write that down. But I mean, like you need also those values here in between. Let's see. UADC peak. Okay, this will not change. This will not change. This will change. This will change, and they will change. Okay. I will discuss that with him. And I think then I will simply write that down in Moodle, but this is a good question. Wait a second, there is a chat, somebody. Okay, question is, how is the data we enter manually in the table? I mean, in the Excel sheet, having our tester data fetched by LT-Spice. For me, it would be nice if you simply fill that table here. Of course, what you could do is if you are able to generate this this graph here, yeah, that you might want, and I think I would prefer that you also make your circles like Professor Banwart did here in here, okay, so that we can compare our expectation against our measurements. That would be nice if you insert that in your report. But regarding like, if you just need to measure the output of the circuitry, or also those values here in between, I think I'll check with him, and then I'll try to give you some explanation here on that. Or have you discussed that in the lecture?
In the lecture, actually, he told.
Yeah.
Yeah, he told like we need to calculate from the measurement like that value, V out 1, V out 2, and V in PP will be calculated based on the voltage divider circuit. It will be the theoretical value.
Yeah. Those first two, they will be calculated from the voltage divider, right?
Yeah.
Okay, and the question here is if they are measured.
Yeah, these two are measured.
Okay, those two are measured, because then this means that for each measurement, you once need to measure here, and then you need to measure here.
Yeah.
Yeah, I'll discuss that with him.
Okay.
Yeah, I'll discuss that with him, and then he will tell you, or I will write that into Moodle. Okay. Okay.
Professor, if it is the case like we have to measure A1 and A2 separately, that means we have to every time change the output pin to the ADC and check it, right?
Theoretically, yes. Yeah. So you could have one round where you measure here, yeah,
okay,
and one round where you measure here, yeah, or at this test point here.
Yeah.
But I will have to check with him if this is like the idea, or if you have to do it just here and then calculate back to the inner values, which also would be possible, but of course it's inaccurate. I'll discuss with him. I'll discuss that with him. Because I mean, like if you, for example, if you would try to replicate that graph here, then this would also mean in order to simply check just the second stage, you would have to bring in your voltage or your stimuli actually in here, right? And to take off the first stage to simply test just the second stage. And I don't think that this is the goal of this assignment. So I'll check that a little bit more in detail with him and let you know.
And Professor, one more question. Like we need to measure V out 2 after 100 ohm resistor or before?
Pardon me, after what?
After 100 ohm resistor or before? Like as you can see in the
after this, that the thing is, this guy has basically infinite or zero impedance, one of those. Basically, if you pull a load in here, it will regulate against it. So you cannot really pull that voltage down. The idea of this resistor here is to limit the current which is flowing into the ADC. Yeah, the ADC has a high impedance, yeah, but it's not infinitely high. So there is some current flowing, and you simply want to protect the ADC by introducing this resistor, but it will not act as a voltage divider. It simply will limit the current.
One more question regarding the table, a little down. The UDAC peak, normally it must be our 40 microvolts, or?
Yes, I would
Okay.
think so.
Okay.
So this would be how I have understood it.
Yeah.
Yeah. I mean, like, yeah.
Professor, like suppose if we configure 40 millivolts, we won't get exactly 40 millivolts in the UDAC peak to peak. We get just half.
But not for the peak. If you
Yeah,
configure here 40 millivolts, then you should get 40 millivolts, and this is like the voltage at the duct. Then the V in peak, then this is half, or not as half. Like this is after your voltage divider. I think, guys, I will do the following. Yeah, I'll clarify all that with him. Yeah, and then maybe write also, or he will explain, or I will write into Moodle like what are those individual things. Okay. And
Okay.
to bring a bit more clarity into that, because it's also not really clear to me. I can check the lecture again, but I'm not sure if this will bring me forward. No. I'll check with him again. Because like this is also for me like the first time we're doing that, and probably also the last time for me. Yay. Yeah. But I'm like, when it comes to giving the points for that, like in the previous assignments, if this is not really your fault or anything, then you will not lose points. No. For me, it's more important that you have like a general understanding of what's going on here. Okay. Good. Then I will stop the recording. And then I would